The first part of Newton's law of inertia is pretty straightforward. An object at rest will stay at rest unless and until it comes in contact with an unbalanced force. That means this baseball isn't going anywhere unless it encounters another force. Say a gust of wind knocks it over, or someone picks it up, like this. The first part of Newton's law of inertia is pretty straightforward. An object at rest will stay at rest unless and until it comes in contact with an unbalanced force. That means this baseball isn't going anywhere unless it encounters another force. Say a gust of wind knocks it over, or someone picks it up, like this. So the ball stays at rest until someone or something moves it or hits it. The second part of the law, an object in motion will stay in motion until it comes into contact with an unbalanced force. Might take a bit more imagination. There are many unbalanced forces in baseball. Friction, gravity, air currents, to name a few. For this example, we can use friction. A grassy infield has a great deal of friction, since grass growing out of the dirt is rough and can be a little bumpy. So if I hit a ground ball, the friction from the field is going to stop the motion pretty quickly. Okay, let's say we're playing this game on ice. Ice is a smooth surface and slicker than grass and dirt, so it has a lot less friction, though it still has some. Less friction, so the ball goes farther before it stops. So what if I hit this ball in a place where there is no unbalanced force at all? No gravity, no air currents, and no friction. With nothing there to stop it, the ball's inertia continues, and the ball stays in motion forever. Law asks what happens when there is no force acting on an object, and the answer is inertia. Newton's second law asks what happens when there is a net force acting on an object, and the answer is acceleration. To be more exact, the law says that acceleration is equal to the net force someone puts on an object divided by the mass of that object. So here's an object, and here's someone who can apply some force. Even though this is a baseball, we're going to put an M for mass on it, because mass is a huge part of this second law. We're going to call the net force the pitcher puts on the ball F, and when the ball leaves the pitcher's hand, it moves with A for acceleration. I'm giving the pitcher the ball, which again is the mass. He's working up some force to put on that mass. Nice pitch, dude. All right, let's get the bowling ball out here.
Huh?
So let's say you put the same amount of force on the bowling ball. What's going to happen?
My arm is gonna fall off?
Ha, no. You're going to put the same force on the bowling ball as you did on the baseball. So that's going to affect the acceleration, right?
Okay, whatever.
Let that force rip, same as before. The bowling ball didn't go as far. Its acceleration dropped, even though the same force was applied to it. Same force, but 50 times the mass. The acceleration drops a lot. Let's write it out. That awesome acceleration you achieved with the baseball, you got that acceleration by throwing the baseball with your net force. If that's a math equation, you're actually dividing the net force you put on the ball by the mass of the ball itself. Then, that not so awesome acceleration you got with the bowling ball, you got that by applying the same net force you put on the baseball onto the bowling ball, which has a mass that is 50 times greater than the mass of the baseball. So if you take the 50 out of this side, you find, yep, the acceleration from the bowling ball pitch is 1/50th the acceleration of the baseball pitch. Much slower. That's Newton's second law in action. Acceleration equals net force divided by mass.
Hey, man.
You two just acted out Newton's third law. My work here is done.
We did?
Yeah, you two exerted equal forces on each other, even though one of you is bigger than the other. And then the two of you went in opposite directions. See what I mean? Maybe not. Okay, let's play it out. So what happened there?
You hit a pretty good fastball.
Actually, the bat hit the ball, and the ball hit the bat. They hit each other with equal opposite force. Take a look. See, the ball is object 1, and the bat is object 2. Object 1 pushes here against object 2, so the ball bends the bat. And object 2 pushes against object 1 with equal force, so the bat bends the ball.
Actually, the bat crushed the ball.
Bend or crush, the point is that the force of the bat on the ball is the same or equal to the force of the ball on the bat.
The force the bat exerts on the ball is equal to the force the ball exerts on the bat. And those forces cause the ball and the bat to go in opposite directions.
Now you get it.
Whenever one object exerts a force on a second object, the second object exerts a force of equal size, but in the opposite direction on the first object.